Okay, so good morning to everyone. So today we continue with lecture 3 of the Holography in Quantum Information course. So in the past two lectures, we have seen some, let's say, basic elements of the idea safety correspondence or holography. That is a weak strong coupling duality between a theory of quantum gravity in asymptotically d+1 dimensional ADS spacetimes and d-dimensional conformal field theories, which roughly we can think has been defined on the conformal boundary of the spacetime. And in particular, we've seen some say basic elements of anti-de Sitter spacetimes and conformal field theory. And so now we would like to let's say be a bit better. How is this equivalence realized? And in particular, what is the dictionary, so the so-called holographic dictionary between these two apparently very different theories. And so this will be the topic of the 3 hours of lectures that we have today. And of course, we won't be able to be exhaustive in that sense, but we will review, let's say, what are, and see together what are the main entries of this dictionary that we will need, well, the main fundamental ones and some that we will need for the rest of the course. And so, as always, so the main reference example or realization of the ADS-CFT correspondence that we will have in mind is the duality between n equal 4 SUN superior means on 4-dimensional Minkowski and type 2B string theory on the Poincaré patch, well, on ADS5 times S5, where the ADS factor is in the Poincaré patch. And clearly, if we believe that this duality extends to, well, to a class of more general theories, I mean, the first, or let's say to more general situations, the first basic predictions that we will can make is that if the conformal field theory is defined on R times S3, this will correspond to taking the ADS factor in global coordinates, so the global ADS. So this is essentially the main reference example that I will use to then try to extrapolate the dictionary to more general theories. And so the first entry of the dictionary that I want to see is the so-called IR-UB connection. So we have seen that gravity in 5-dimensional anti-de Sitter space is somehow related through the holographic principle to n equal 4 superior meals, living in one spatial dimension less, so in 3+1 dimensions. And now we would like to see, let's say, what is the other direction, that is, how can we interpret this extra dimension from the quantum field theory point of view. And essentially, we have already seen what the answer is when we took the low energy limit of the two perspectives on D3 brains. So for that, recall that we had seen that the back reaction of a stack of n coincident D3 brains on the geometry would lead to a spacetime which has, let's say, pictorially this form in which we have asymptotically 10-dimensional Minkowski and a throat, an infinite throat that develops as we approach what was the location of the D3 brains in spacetime. And so, so this, let's say, that's going down the throat was going towards are equal 0, where the original D branes were located. And in particular, we are seeing that as we move in the radial direction towards r equals 0, this corresponds to lowering the energy measured by an asymptotic observer. And so essentially we have already seen that this extra radial direction, which appears in the gravitational description, is somehow interpreted as the energy scale in superior Mills. And so let's review a bit better this argument and try to make it a bit more precise. And so for that, let's take the Poincare patch of ADS. So let me recall what the metric is. So capital R is the ADS radius. And let me write it in the Z coordinates, which we introduced. For which the boundary of ADS is at Z going to 0. And so here T and X define the boundary units in the superior Mill theory. So now local proper time and local proper distance at the same radial location Z are the following. So d tau is defined as R over Z dt, and the L is R over Z dz. Sorry, the X. And so the relation between energies and distances on the boundary and in the bulk is the following. So the energy in superior Mills, Z over R, the local energy in the bulk, and distances in superior Mills, I'm just writing a Mills for simplicity, will be, what did I do? I put the, sorry, I put it the opposite. R over Z and Z over R, the local. Okay, so that's the relation between energies and distances as measured in the bulk and in the conformal field theory. And so if we look at the same bulk process, so we have a fixed local energy and distance, and this process takes place at different radial locations, we will have that the energy as measured in the superior Mills theory will be given by 1 over Z, well, R E local. And so essentially it will be proportional to 1 over Z. And similarly for the Young Mills, so this will be proportional to Z. And so we see that if we send Z to 0, so if we approach the boundary, this will correspond to large energies as measured in the boundary theories and short distances. So from the superior Mills point of view, this is a UV process. And similarly, if we approach the interior of the bulk, we have the vice versa. So the energy will go to 0, will diverge. And so this is a IR process in the boundary theory. But from the ADS point of view, going to z equals 0, so approaching the boundary actually means going to large distances, and so this corresponds to the IR in the bulk. And similarly, going to the interior corresponds to the UV from the bulk point of view. And so we see how this IR UV connection arises. So the UV or IR in ADS corresponds to the, like I said, UV IR corresponds to the IR and UV in the boundary conformality theory. And so, and moreover, since, let's say, a typical gravitational process in the bulk will have an energy. So a local proper energy will be fixed by the ADS scale 1 over L or 1 over R. We really have that the energy in Yang-Mills is essentially given by the inverse of the radial bulk coordinate, and similarly for the spatial scale. And so this is known as the energy radial radius relation. And so essentially we see that the energy of the boundary theory corresponds to the depth in the bulk. So this relation really geometrizes the notion of energy and shows how this extra radial direction emerges from the boundary point of view. And so as we said, this geometrizes the notion of energy and does also somehow geometrizes, so evolving in the radial direction also geometrizes the notion of renormalization group flow. So since the boundary of ADS is at infinite distance, as we have seen, let me make a remark. So it's often necessary to introduce a bulk infrared cutoff to regularize computations in ADS. So IR cutoff in ADS. And so this is achieved by simply placing the boundary at some finite distance, epsilon, with epsilon going to 0. And so on the boundary, this regularization process by the IR-UV connection corresponds to introducing a UV cutoff in the boundary theory. So a short distance cutoff for energy cutoff at 1 over epsilon. Okay, let me also make another observation so related to this point. So in a conformal field theory on Minkowski, there are no scales, and so that means that there are excitations of arbitrary low energy. And so indeed, this corresponds from the bulk point of view to the fact that the interior of the bulk spacetime extends all the way to Z going to infinity. So no scales. At infinite proper distance. On the other hand, if our theory has an energy gap, Then the bulk needs to end smoothly at some finite proper distance, z equals z naught. So, so if you have an energy gap, then the bulk will end at some finite proper distance z naught, which is can be related, for instance, to the inverse temperature or to some inverse mass. And so this is the case, for instance, of well, one of our two main examples. So for a conformal field theory on R times S3, there is a mass gap because the sphere, well, the S3 factor is compact. And so, so this we know corresponds to gravity in global ADS5. And indeed, if we recall from what we saw in the Carter, well, for the causal structure of global ADS, in that case, the center of the cylinder is at finite proper distance from the boundary. Well, let me just write it. Okay. So this was the very basic observation, well, we can make about how to relate quantities in the two theories. And let me recall that also last time we'd also seen how to relate parameters in the two theories. So now I want to talk about symmetries. And again, let's start from the main example and extrapolate from there. So on the one hand, we have n equal 4 superior means. And on the other side, we have type 2b string theory on ADS5. And so what are the symmetries of the two and how do they match? So we saw most of it already. So for n equals 4 superior means, we have a conformal symmetry, which is a global symmetry of spacetime. Which is an SO4, 2. And that we saw corresponds to the isometries of ADS5. SO4, 2. And so since isometries are a subgroup of diffeomorphism, these are local symmetries from the bulk point of view, which are related to a global symmetry on the boundary theory. Then we have, as we saw, a global internal SO6 symmetry. Which from the bulk point of view reflects into the isometries of the S5 factor. And so again, we have a global boundary symmetry, which relates to a local bulk symmetry. And finally, well, we have supersymmetry. And well, let me not be too specific. In any case, we have global supersymmetry on the boundary theory, which relates to the same amount of local supersymmetry in the bulk. And so the pattern, I guess it's clear. So on the left-hand side, for this boundary theory, all symmetries that we're talking about are global symmetry. And on the right-hand side, we have this reflects into local symmetries. And so essentially the key relation for the ADS-CFT is that global symmetries in the conformal field theory corresponds to local symmetries in the gravity theory. And right, so let me make a couple of observations. So the first one is what is so special, let's say, about isometries, which are, let's say, the one that are reflected in the boundary theory. So we have the whole group of diffeomorphism, but it's this subgroup which is particularly important. And so this is the case because this is the subgroup of diffeomorphism which leaves invariant the asymptotic bulk metric. So it leaves invariant the boundary metric, but it allows the bulk to fluctuate. And so essentially these are known also as large gauge transformations, and are those diffeomorphisms that decay rapidly enough at the boundary. And let's say roughly we can consider them as the global part of the diffeomorphism. And the other observation that I want to make, and this I guess I will write it schematically, is that as you see the SUN symmetry, so the SUN gauge symmetry of the conformal field theory has no counterpart in the DS, and this is clearly understood because being a gauge symmetry, it simply describes the redundancies of the theory, and that's why it has no physical counterpart. And so let me write what do we expect in general. So for a conformal field theory in Minkowski in the dimension, which is dual to a gravity theory in ADS B+1. In general, we have the following. So the conformal symmetry, so D, 2 will map to the ADS isometries. So local SOD, 2. Then if we have some global internal symmetry, so for instance, a global U1, let's say, this will map to a gauge symmetry in the bulk. So, U1, and finally, if we also have supersymmetry, some amount of global supersymmetry, this will map to the same amount of local supersymmetry. And so that's what is realized in general. Good. Okay, so let's move to the next fundamental entry of the dictionary, which is the so-called field operator correspondence. Sorry. And for that, we will restrict to the semi-classical gravity limit that we have discussed at length in the previous lectures. So essentially, we are doing a quantum field theory in some curved background. So we will, as I said as before, we will start from our reference example and then try to extrapolate to the dictionary to general dualities. So this is an equivalence between two theories. So clearly there must exist a relation, a correspondence between Hilbert spaces. So let me write schematically what we expect on the boundary. So for the boundary theory, and what do we expect from the bulk ADS theory. So, well, what we have seen is that the boundary conformal field theory, well, the Hilbert space, sorry, of the boundary conformal field theory is organized in the in representations of the conformal group. So SOD, comma 2. And from the bulk point of view, the Hilbert space is organized in representations of the isometries of SOD, comma 2. And so the main objects in the representation on the left-hand side are local gauge invariant operators. And on the right-hand side, we have bulk fields. So let me write schematically what is the relation that we do expect between operators in the boundary conformal theory and fields in the bulk, and then we will see a bit better why this is the case and motivate it. So, so we do expect that, well, here I'm always talking, as we said, about gauge invariant operators because the SUN gauge symmetry is not visible from the bulk point of view. So okay, I say it once and for all, I won't repeat it every time. So that is to say that, so scalar operators O corresponds to bulk scalar fields. Some vector operators J mu will correspond to vector fields in the bulk. So of course we have to match quantum numbers. And let me use so mu for bulk indices and m. Sorry, for boundary indices and m for bulk indices. And like tensor operators, like the basic one in the conformal field theory, which is T mu nu, the energy momentum tensor, will correspond to tensor fields. And well, as we will motivate, in fact, this corresponds to the metric itself. And so in general, if there are, so this is just to give like the main examples. In general, if there are other symmetries, like a global symmetry or supersymmetry, the quantum numbers and the representations under those, they also have match. And so, okay, so let's now come to our main example. So type 2B supergravity on ADS5 times S5. So I'm talking about supergravity because remember, I'm always looking at the semi-classical gravity limit now. And so the spectrum of type 2B supergravity on ADS5 times S5 is known since long. And indeed, all counterparts of the spectrum have been found in the dual n=4 super-Yamil's theory. And so let me just state what are the main match, let's say, pairing in this in the spectrum of these two theories. So the all n=4 Lagrangian, which is itself a local operator, corresponds to the dilaton. Then the SO6 conserved current, let me write it J mu, A, corresponds to SO6 gauge fields, which are obtained from the dimensional reduction on the compact S5. And well, so this is essentially its matches what with the general intuition that we wrote before. And indeed, the energy momentum tensor, mu, can be found to correspond to the metric perturbations HMN, so the deviations from ADS spacetime. And so this last point is clearly natural from the mathematical point of view, since we are pairing symmetric tensors, but it's also very natural from the physical point of view, as we will comment on in a moment. Okay, so let's develop a bit further on these field operator relations. And so let's start from the quantum field theory point of view. So if you have an operator O in a quantum field theory, it's natural, well, one natural operation that one can consider is to perform a deformation of the theory. So we start with some T, and then we deform the theory by adding a source for this local operator. So phi naught here denotes a source for the local operator of the theory. And so if this is constant, this type of deformation essentially simply amounts to changing the coupling which appears in O. Because remember that in general, this local operator is a product of fields and of their derivatives. And so such an operation changes the coupling. And so we would like to understand what does this natural operation that we can perform in the bulk perspective. What does it correspond to in the bulk perspective? And so to understand it, we will consider again the familiar reference example and extrapolate from there. So in type 2b supergravity, the coupling G string is given by the expectation value of the dilaton. And so in a spacetime with a boundary, such as anti-de Sitter space, it's natural to identify the expectation value of phi with, let me call it phi naught, which is the boundary value of the field. And so that's because we can assume that the field doesn't fluctuate on the boundary, and thus this boundary value sets its expectation value. And well, remember that using the relation between parameters, so fact that G and mil squared is given by 4 pi G string, we then have that this is 4 pi e to the phi naught, where phi naught is the boundary value of the dilaton. And if we now also observe that from the boundary point of view, the coupling constant itself, G and mil squared, can be considered as a unimorphism source, so something of this type, for the entire n equal 4 Lagrangian. So in this case, the operator O would be the entire Lagrangian. And so taking a deformation of this type star on the boundary then means doing the following operation. So let's take the action for n equal 4, and then we deform it by changing the dilaton boundary value. So essentially we go from phi naught to phi naught plus delta phi naught, and thus the action changes in this way to the first order, and then we have again the integral of the n equal 4 Lagrangian. And thus, so for this, from this point of view, so that makes it clear that let's say that the bulk dilaton field phi corresponds to the boundary operator, so the entire n equal 4 Lagrangian, and as we saw, this can also be deduced by comparing the spectrum of the two theories and from symmetry consideration, and that so from the well, and then performing a deformation corresponds to changing the asymptotic boundary value of the bulk field. So trying to extrapolate from this example, we see that a deformation of the boundary theory for a local operator O with a source phi naught essentially corresponds to a bulk field phi, which corresponds to the boundary operator O of X, and which has a boundary value, phi naught. So we can think of the boundary value of the bulk field, which is dual, which corresponds to the local operator O, as a source for the local operator itself. And this was an example that we extrapolated, let's say, from the dilaton Lagrangian relation to scalar operators and scalar fields in the bulk. And this clearly extends to other fields, like, let's see, going a bit slow. So let me just write it schematically. So similarly, we can expect that, and there are similar arguments to see that for a conserved current on the boundary, J mu, this corresponds to a bulk gauge field AM, and in particular that, well, as we saw, this global symmetry corresponds to a gauge symmetry in the bulk. And right, and similarly, that if we turn on a deformation and as a source for this current in the boundary theory, this source corresponds to the boundary value of the dual gauge field. And similar, there are arguments to show also that the energy momentum tensor of the conformal field theory corresponds to perturbations of the matrix in the bulk. But okay, since I'm going a bit slow, I will skip these arguments. So let's just trust, let's say, that this relation that we kind of, for which we saw some heuristic argument for scalars, can be similarly extrapolated for currents and for the energy momentum tensor. And in that regard, for the last point, let me just make one observation. So the energy momentum tensor is a basic contribution of any conformal field theory, and thus by this relation, we see immediately that the bulk dual theory has to be a theory of gravity. So the bulk theory needs to have, since any conformal field theory has an energy momentum tensor. Okay, I'm sorry if that was maybe a bit fast. I mean, I don't know how familiar you are with these ingredients, but yeah, as usual, ask if you have questions. In any case, I can stay a bit longer at the end, and also, okay, we have 2 more hours in the afternoon, so yeah, just ask questions, please. Okay, so in the last minutes, I think I will exceed a bit noon since we started later, maybe some a few more minutes. So the next ingredient that I want to introduce is the so-called mass conformal dimension relation. So continue to be to make it precise, this equivalence. So we have seen, essentially what we just tried to see was that, or to motivate, was that a boundary local operator O, let's stick with scalars, corresponds to some bulk field phi, which has the well, same quantum numbers. And now what we would like to ask is how does the conformal dimension of the operator, which we saw is basic ingredients to classify representations, how does it map in the bulk? So how is delta related? What is delta related to? And what we'll see is that this reflects in the mass of the bulk field. And the other point that we want to see is, so this bulk field can be expanded in modes as usual in ADS, and we want to see what these modes relate to from the boundary point of view. Okay, so these are the two points that I want to see now, and I guess we will probably see just parts of them for this lecture, and then we will continue in the afternoon. So, so to see it, let's consider the gravity side. Let's consider a generic form for the bulk action. So this generically will be of the following form. So this is just G Newton times some numerical factors in d+1 dimensions. And so we will have the Einstein-Hilbert term, a negative cosmological constant, and some matter Lagrangian, which will depend on the specific realization that we are considering. And so typically this Lagrangian will contain terms of the following type. So let's say that we have a scalar phi, which is the example we are doing here. So we will have a kinetic term, a mass, and some generic potential, which includes all known linear terms. And then in general, we will have also other fields like Maxwell fields and so on. But let me just focus this scalar, one single scalar contribution as an example. And so, so now we can consider fluctuations of the scalar and of the metric around empty ADS. And so for that, it's actually convenient to use a canonical normalization of the kinetic term. So to reabsorb this prefactor, which goes like 1 over G Newton in the normalization of the kinetic term. So we will write that phi is kappa phi prime. So phi prime, okay, so in the background, clearly there is no scalar. So the background is empty ADS, so all fields vanish. And so this gives us some canonically normalized fluctuations for the scalar. And we also consider some fluctuations for the metric. So here we do have a background, which is empty ADS, which is 0. And then we take some canonically normalized fluctuations, HMN. Okay, and so now recall that so kappa squared well, yeah, it's proportional to G Newton in d plus 1 dimensions, which in units of the curvature radius, we saw scales like n to the minus 2 in our favorite super-Yamil's example, or type 2B string theory example. And thus, as we take n large, which is the limit in which we are working, since we are interested in the semi-classical gravity limit, this goes to 0. And so if we take fields or fluctuations of the fields, so prime and Hn, which are order 1, well, we see that clearly like quadratic terms, one scale, once we canonically normalize one scale with kappa, but higher order terms will. So for instance, like a cubic interaction which might appear in the potential with scale like with kappa, and thus will vanish in the kappa to 0 limit. So essentially, this is just to say that at leading order in this large n expansion, we can just work with a quadratic action for L matter. Which is a free theory in ADS. And this is actually enough for all considerations that we need to make now. And so let's continue with this scalar field example for illustrative purposes. And so let me write again the bulk quadratic action for our scalar phi. And let me drop the prime here. So now phi is the canonically normalized field. And then we have all the higher orders in kappa, which we are here neglecting. And here G is what I called G0. I'm also dropping the 0. So this is the metric of the ADS background, which is the ADS Poincare patch. Which, since it might be useful, I will actually copy before. Okay. And so what we want to do now is to quantize this free theory in this curved ADS background. So first thing to do is clearly to solve the equations of motion. And so exploiting, let me see actually what is a good point. Yeah, I need, let's say, 5 maximum more minutes, and then I will stop. And so, so exploiting translational invariance in the x direction, we can make the following Fourier transform ansatz for the field phi. So we write phi of z and x so, okay. And so if we substitute these ansatz, very familiar in the equations of motion, we are only left with z derivatives. And let me write the equation since we will need it. So the equation takes the following form, as you can easily verify on explicit computation. And so this equation can be solved actually exactly. And one can find a complete basis of solution. And then to quantize the theory, as usual, we will expand the scalar in terms of this solution, and then promote the coefficients of this expansion to creation and annihilation operators. And actually, we will comment a bit more about this later, because we will need, well, we will want to see what are these modes of the bulk field from the boundary point of view. But for the moment, we actually do not need to solve exactly this equation. So what we are just interested in, or what we just need for the moment, is to consider the asymptotic behavior of the field close to the ADS boundary. So for the moment, we just look at how does this solution, or well, equation and the solution, behave as z goes 0. So in that case, we can simply neglect this term, which is clearly subleading with respect to the mass term. And so this equation simplifies, and it's simply, well, it's an homogeneous equation which is simply solved by a power function. And so the solution is simply of this form. So it's some power of z, which I'm calling delta with some insight, but for the moment, this is not related to the operator conformal dimension. It's some generic power. And so if we substitute in the equation, we just find a quadratic equation for delta, and the solutions are delta equal to d over 2 plus or minus the square root of d square over 4 plus m square r squared. And so let me introduce this notation. So we will write actually delta as d over, okay, so these are the two solutions. And so in the following, we will call delta the plus solution, so d over 2 plus nu, where nu is this square root, and we will call delta minus the other solution, so d over 2 minus nu, which is equal to d minus delta. And so then, and then I will stop. We see that the behavior of our scalar field near the asymptotic boundary of our spacetime as z goes to 0 is the following. So this is the, for the Fourier components of the field, it will be like a, z to the d minus delta. So A is a generic coefficient, and similarly for B, z to the delta plus other terms. And in particular, notice that this is the dominant term close to the boundary, and that this power law behavior is subleading. And equivalently, in coordinate space, let me just erase the K, we can write the same type of expansion. So let's just Fourier transform. And so this is the behavior of the scalar bulk field close to the boundary. And okay, it's not maybe the most natural point to stop, but since it's already quite late and I'm sure you're tired, I will stop here, and then we will continue in the afternoon. So.